Welcome. In this video, we're going to continue taking a look at the relationships between angular and linear motion, and this time we're going to take a look at the tangential velocity. So to start us off looking at velocity, we're going to take a step back and talk again about arc length that we talked in the previous video. So let's say we have a disk like this gray disk, and it's going to be rotating, and we're interested in a point on that disk, that yellow point. So the disk is going to be rotating at some angular velocity, omega, so the whole disk is rotating, and if it goes through a certain amount of rotation, the distance that point will travel will be the arc length, and that'll be equal to the radius, or the distance from the center of rotation, multiplied by the amount of rotation, or the angular displacement. We've seen that formula before. So if we're going to think about what is the velocity of that yellow point, it's actually just as simple as saying, well, we know that velocity is distance over time, or how much the change in distance is over the change in time. So we could actually just assume that the velocity of that point might look something like this. So the change in position, or the arc length, divided by the time. So if we start with that formula for what the velocity of that point might be, we can take a look, and we know that the arc length is actually the radius times the angular displacement. So we can substitute that in for arc length, and we get this formula. And now when we take a look at that version of the equation, we can see that we have angular displacement over time, and we know that formula, angular displacement over time, is simply just the angular velocity. So we can substitute the angular velocity there, and we end up with this formula. So we know that the velocity of that point is equal to the radius, or how far that point is away from the center of rotation, multiplied by the angular velocity, or how fast that object is rotating. So that gives us a relationship between the velocity of that point and the angular motion of the object. But the question that we haven't answered with this is, what direction is that velocity going? So in order to answer that, we have to set up another type of coordinate system. And we're going to set up a coordinate system that's going to be centered around the point that we're interested on the object. And so we'll set it up like this. So we'll set one axis of that coordinate system that goes from the center of rotation out along the radius pointing outwards, so parallel to the radius. And then we'll set up a second axis that's perpendicular to that, 90 degrees, since we want to have an orthogonal coordinate system. So those two axes would look like this. So the one that's pointing from the radius out would be that blue one, and the one that's 90 degrees to that, or perpendicular to that, would be the red one. And we'll give those axes names. We'll call the one that's parallel to the radius, we'll call that the radial axis. That makes sense. And the axis that's perpendicular to that, we'll call that the tangential axis. And one of the reasons it's called the tangential axis is if you look at the line, you notice that it's tangent to the circular path that the point would make. Quite often, that tangential axis is also called the transverse axis, and I might call it transverse sometimes, and it's called transverse in some of the problem sets, but they mean exactly the same thing. So the tangential axis is the same thing as the transverse axis. And this axis, or this coordinate system, is a little bit different than some of the other ones we were looking at, in that we're going to fix this coordinate system to the point. So it's going to move with the point as the object rotates. So something like this. So if we're interested in the point on the edge of that green circle, and the green circle is rotating, the coordinate system would rotate with the point, would be fixed to the point, and always pointing. The radial axis would always be pointing out from the center of rotation, and the tangential axis would always be 90 degrees to that. So again, if the object rotates, the coordinate systems are going to rotate with it. So if we've set up this coordinate system, it turns out that the velocity that we calculated earlier goes along the tangential axis, and it always goes along the tangential axis. And as long as the radius remains constant, then that'll always be the case. And in everything we're going to look at in this class, the radius, or the distance from the center of rotation, is always going to stay the same. And so the tangential, or the transverse velocity, will always point in the tangential axis. The other thing to note with this formula is that the units for the angular velocity, units for omega, they have to be in radians per second. So just like the units for angular displacement when we're calculating arc length had to be in radians, the units for angular velocity here have to be in radians per second. So just like we looked at before, if the object is spinning and we're interested in the point on the edge of that green circle, and the yellow arrow would be the transverse or the tangential velocity, and as the object rotated, the velocity always points in that direction, in that tangential direction. So we can take a look at maybe a simple numerical example just to take a look at what that might look like. So in this example, we have a hockey player taking a shot, and his stick is rotating at this point in time at 1700 degrees per second. And the blade of the stick, the end of the stick, is located 1.2 meters from the center of rotation, from the axis of rotation. And the question is asking, what is the linear velocity of the blade at impact? In other words, what is that transverse or the tangential velocity of the blade just before it hits the puck? So if we draw a diagram of that question, we can see that this is kind of a sideways view of the stick just before it hits the puck, and the stick is rotating at 1700 degrees per second in kind of that direction, and the point that we're interested, the end of the blade, is 1.2 meters from the center of rotation, and we're interested in the velocity right there, right at the end of the stick. And because we know that the velocity is going to be in the tangential direction, we're looking for this velocity, so the red arrow down there. So it'll be the transverse or tangential velocity. And so that formula says we just take the radius and multiply it by the angular velocity. But in this case, the angular velocity is in degrees per second, and we can't use that in the formula the way it is. So we need to convert the angular velocity into radians per second. And like we've seen in previous videos, there's a number of different ways to do that. I always like to multiply by pi over 180. And so we'll take 1700 degrees per second multiplied by pi over 180 gets us about 29.7 radians per second. So that's the angular velocity of the stick in radians per second. So now we can use that in the formula. So we say the tangential velocity of the end of the stick is equal to the radius times the angular velocity, which would be 1.2 meters times 29.7 radians per second, which gets us 35.6 meters per second. So in other words, the transverse or tangential velocity of the end of that stick is 35 meters per second. Now you notice this is a linear velocity, so it's the linear velocity at that point. It's in meters per second. The stick is rotating at 29.7 radians per second. That's the angular velocity of the stick. But the linear velocity of that particular point on the stick, that's 1.2 meters from the center of rotation, is 35.6 meters per second. So if you remember then that the tangential velocity, if you look at the formula there, is not only dependent on the angular velocity, but it's dependent on how far you are from the center of rotation or the radius. So you can have multiple points on the same rotating object that will all have different tangential velocities. So in this case, we've got our same green circle again. It's going to rotate, and we're looking at 3 different points on that object. And the yellow arrows are proportional to the tangential velocity that those points would be experiencing. So the object's rotating. All 3 points are rotating with the object, but they'll all have different tangential velocities because they're all at different distances from the center of rotation. One of the practical applications of transverse or tangential velocity is in some sport applications. So we saw the hockey stick example a little bit earlier. Golf is very similar. So in golf, if you want to hit the ball really far, you have to maximize the club head speed, or in other words, the tangential velocity of the club head, which is a point on the club. And now that we know that the tangential velocity is related to 2 things, basically those are the 2 things you can do if you want to increase the club head speed or increase the tangential velocity. You can either increase the angular velocity, so how fast you're rotating the club, or you can increase the radius, or how far away the club head is from the center of rotation. And that's the reason why the club that's used to hit the farthest, in other words the driver, is the longest club in the bag. So if If you have a short club and a long club and they're both rotating with the same angular velocity, the long club, which has the club head farther away from the center of rotation, will have a larger tangential velocity.